Hello and welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is there, so feel free to share that in the comments. And if you'd like more episodes like this, you can always subscribe. It helps us keep drifting together through these quiet corners of science. Now, picture a child in a garden holding a small plastic wand dipped into soapy water. They take a slow breath, blow gently, and a perfect sphere rises into the air. It floats, weightless, a trembling skin of liquid that shimmers with shifting bands of color, blues sliding into gold, green melting into violet. For a moment it seems impossibly delicate, impossibly beautiful. And then, with the softest sound, it vanishes. It seems like nothing, a toy, a distraction on a summer afternoon. But hidden in that fragile globe are centuries of science. Why does it choose to be round? Why does it shine with such fleeting colors? Why does it always collapse in the end? For generations, physicists and mathematicians leaned close to soap bubbles, not because they were frivolous, but because inside them were clues to how the world works. From the pull of surface tension to the dance of light waves, bubbles became a lesson in how the smallest, most ordinary things can reveal the deepest truths. And tonight, we'll drift into that world together. When you watch a soap bubble float into the air, the first thing you notice is its shape. No matter how clumsy the breath that created it, no matter how uneven the film, it settles into a sphere. Always round, always the same. It doesn't matter if the bubble is small, trembling on the edge of the wand, or a great wobbling globe drifting away. The choice is the same: roundness. The explanation begins with something invisible, something happening at the very edge of the liquid: surface tension. Water is made of molecules that cling to each other, pulled together by weak electric attractions. Inside the bulk of a droplet, each molecule is surrounded equally, tugged in all directions. But at the surface, the molecules are exposed on one side, and that balance breaks. With nothing above them, they feel a one-sided pull back into the liquid. The effect is like an invisible skin, stretched tight, always pulling inward. We call it surface tension. When air is trapped inside a film of soapy water, that tension sets to work immediately. It tightens, shrinks, pulls, and the film adjusts itself until the force is balanced in every direction. The outcome is the simplest, most economical geometry possible: a sphere. Among all possible shapes, the sphere encloses the greatest volume with the least surface area. And because nature tends to economy, it is the form surface tension chooses without hesitation. This property belongs to a family of shapes mathematicians call minimal surfaces, surfaces that achieve a balance between enclosing space and minimizing boundary. Soap bubbles are not the only examples. Catenoids, helicoids, and other strange forms appear when you dip twisted wires into soap solution, the films spanning them like ghostly sculptures. But the sphere is the most familiar. It is the answer a bubble gives when asked silently, "How can you exist with the least effort?" In the 19th century, one scientist devoted himself to these fragile forms almost to the point of obsession. His name was Joseph Plateau, a Belgian physicist. He was born in 1801, and by the mid-1800s he had made soap films his life's work. Plateau wanted to know how these thin surfaces arranged themselves, what rules they obeyed. He experimented with wires bent into every shape: squares, spirals, circles within circles. He dipped them into soapy water, held them up to the light, and watched as the films stretched and shifted, settling into delicate geometries. The sight entranced him. The shimmering skins seemed to obey laws deeper than chance. He studied them tirelessly, sketching, measuring, recording what angles the films formed where they met. To see better, he often used intense light, staring through the bright glare of interference colors. Over years, this habit damaged his eyes. Eventually, he lost his sight almost entirely. Yet even after blindness, he continued to study soap films with the help of assistants. He could no longer see the bubbles himself, but he knew from memory and mathematics what must be there. From these experiments, Plateau distilled a set of elegant rules, now known as Plateau's laws. They describe how soap films always behave, whether stretched across wires or gathered into clusters of bubbles. The first rule: soap films are always smooth surfaces, never rough or jagged. The second: when three films meet, they do so at angles of exactly 120 degrees, like the thirds of a perfect circle. The third: when four edges meet, they form a tetrahedral angle of 109.5 degrees, the same geometry later discovered at the heart of carbon chemistry. These rules might seem almost decorative, but they revealed a truth. Soap films obeyed strict mathematical laws, as precise as those governing crystals or planets. What looked like a child's toy was in fact a natural solution to problems mathematicians struggled to calculate. To this day, computer algorithms that search for efficient surfaces borrow inspiration from Plateau's experiments. Architects and engineers, designing structures that must be light yet strong, study the forms bubbles create. Plateau's legacy is still alive in every curved roof that minimizes material while enclosing great spaces. Once you see it, the logic of roundness reveals itself everywhere. Raindrops gather into spheres as they fall, pulled tight by their own surface tension, only flattening when air resistance presses against them. On the waxy leaves of plants, beads of water sit like crystal marbles after a storm, refusing to spread. Oil spilled on water clumps into droplets, each one rounding itself into a tight bead. In orbit, astronauts playing with globules of water watch them form into floating spheres, untouched by gravity. The bubble is only one variation in this wider family of shapes chosen by tension and efficiency. And yet, there is something special about the bubble. A droplet is full, but a bubble is hollow. It is air wrapped in liquid skin. Its roundness is the result of a delicate balance between the pressure inside and the pull of the surface outside. This balance is so finely tuned that the smallest disturbance, a grain of dust, a patch of dryness, a finger that touches too firmly, will collapse it. The bubble bursts. What remains is nothing but dampness in the air. This tension between strength and fragility is part of its fascination. In the moment before it vanishes, a bubble demonstrates geometry with more precision than any drawing. It is a model of balance, a natural diagram of efficiency, a proof carried by molecules. For Plateau, this paradox was irresistible. He devoted his sight to it. He gave his eyes to the study of thin films, convinced that something in their fleeting beauty carried lessons worth learning, and perhaps he was right. Because when we see a child blowing bubbles on a summer afternoon, we are not only watching a game, we are seeing surface tension made visible. We are seeing geometry solved in an instant. We are seeing laws of physics that govern planets and stars, distilled into a fragile sphere floating through the air. It is an ordinary wonder, easily overlooked, and yet the entire logic of its shape is a story, one of invisible molecular pulls, of mathematicians searching for minimal surfaces, of a blind physicist who gave his life to films of soap and water. Roundness is not trivial. It is the quiet signature of nature's preference for economy, revealed in the shimmer of a bubble. A soap bubble drifts into the air, and the first thing that catches the eye after its roundness is its shifting skin of color. Bands of green slide into violet. Orange glows beside blue. Sometimes the entire surface shimmers with a rainbow that seems alive. These colors are not painted on. They are not pigments hiding in the film. They are the product of light itself, a trick played by the thinness of the bubble's skin. The secret lies in interference. Light is a wave, though it took centuries of argument for science to accept this. When a wave strikes the thin surface of a soap bubble, part of it bounces back from the outer layer. The rest travels a tiny distance deeper, reflects from the inner layer of the film, and comes back out. These two reflections overlap. Sometimes their peaks line up and reinforce one another, creating brightness. Sometimes a peak meets a trough, and they cancel, creating darkness. The result is a shifting spectrum of colors, each one strengthened or erased, depending on the thickness of the film at that exact point. Because the bubble's skin is not uniform, always flowing, draining, thinning under gravity, the thickness varies constantly, and so the colors move. A patch of green slides across the surface, fades into red, then disappears into nothing. What we see is the dance of wavelengths interfering with themselves, guided by a film only millionths of a millimeter thick. At certain thicknesses, some colors vanish completely. Around 1/4 of a wavelength of visible light, roughly 150 nanometers, destructive interference wipes out particular hues. This is why the palette seems to shift in bands, as if the bubble is striped with invisible rulers. To the eye, it looks like an unpredictable rainbow. To physics, it is as orderly as mathematics. The fascination with these shifting colors is not new. In the 17th century, Isaac Newton himself spent years studying thin films. He pressed a convex lens against a flat glass plate, trapping a thin air film between them, and observed the concentric rings of color that appeared. Today, we call them Newton's rings. At the time, Newton did not believe in light as a wave. He considered light to be made of particles, or corpuscles, yet he carefully recorded the colored rings, unable to deny their patterned beauty. His notes show a mind torn between theory and observation, seeing wave-like interference even while doubting the wave nature of light. A century later, in 1801, Thomas Young gave the most famous demonstration in physics, the double-slit experiment. By passing light through two narrow slits and watching the overlapping ripples of brightness and darkness, he proved that light behaved like a wave. Around the same time, soap films became a favorite tool for illustrating this truth. They were fragile, fleeting laboratories. A film stretched across a frame showed interference colors as clearly as any experiment in optics. In classrooms and lecture halls, bubbles glowed not only with beauty, but with evidence. What makes these colors so remarkable is their dependence on thickness measured in nanometers. A soap bubble, only a few microns thick, 1/100th the thickness of a human hair, can display the full spectrum of visible light. As the film drains thinner at the top, gravity pulls liquid downward, and the color bands slide. Eventually, at the thinnest point, something curious happens. The colors vanish. The bubble patch turns black. This black patch is the harbinger of the bubble's death. At that point, the film has become so thin, just a few nanometers, thinner than the width of a soap molecule itself, that no visible light can interfere within it. The film is practically gone. Soon after, it breaks. To the eye, the dark spot is a warning. The shimmer is about to end. It is a quiet reminder of how fragile the structure is. A soap bubble may look vivid and alive, but its life is measured in seconds. Its beauty is created by the very process of vanishing, as its skin drains thinner and thinner until the colors collapse into darkness. For physicists, though, these vanishing films have been anything but trivial. The study of interference in thin films became a gateway to understanding optics. It helped confirm that light was not a stream of particles alone, but carried wave properties. Later, in the 19th and early 20th centuries, experiments on thin films guided the development of spectroscopy, the analysis of light split into colors. Soap bubbles, children's toys of summer afternoons, helped sharpen the very tools with which we analyze stars and galaxies. The beauty of interference is that it links the everyday to the cosmic. The The same physics that makes colors swirl on a bubble's skin is at work in the iridescence of oil spills, in the gleam of a beetle's shell, in the rainbow sheen of a butterfly's wing. It is also present in the coatings on lenses, where scientists learn to control interference by applying layers of specific thickness to reduce glare. A simple soap film, unstable and fleeting, provided the first hints that guided technologies we still rely on every day. Even more curious is the way these films influenced mathematics. The changing colors correspond to precise thicknesses, and physicists learned to calculate them. Each shade, each band of brightness, corresponded to fractions of a wavelength. The bubble became a natural ruler, measuring invisible distances with light itself. When Joseph Plateau watched bubbles with such intensity in the 1800s, he wasn't only seeing their shapes, he was also witnessing interference patterns that encoded thickness on the nanometer scale, centuries before the term nanometer was coined. The thin film teaches patience. Its colors move slowly, unpredictably, as the liquid drains. To sit and watch a bubble is to watch physics unfold in real time. The top darkens, the colors slide downward like ribbons, and finally, the inevitable burst. But in those moments of fragility, light waves are performing their quiet dance, layering and cancelling, writing invisible arithmetic across the air. What is striking is how easily overlooked all this can be. To most, the colors are just decoration. To a physicist, they are proof of interference, precision instruments masquerading as toys. To Newton, they were uncomfortable evidence that light had properties he could not fully fit into his theory. To Young, they were confirmation of waves, and to us, they are a chance to see the invisible world revealed for just a moment before it disappears. So when you catch sight of a soap bubble in sunlight, remember that you are not only watching a rainbow drift across a sphere of air. You are watching light split itself, overlap itself, and cancel itself, guided by a film just a few hundred molecules thick. You are watching the same physics that glitters on beetle shells, that paints oil slicks on pavement, that engineers use to coat camera lenses and astronomers use to read the light of stars. And when the top of the bubble turns dark, when the shimmer gives way to black, you are witnessing something even rarer. The thinnest surface you will ever see with your naked eyes. A film so slim it is almost not there, and yet for a heartbeat, it holds the rainbow in place. The soap bubble, fragile and fleeting, offers us not just color, but clarity. It shows us that the world's most delicate surfaces can reveal the strongest truths, that beauty and physics, fragility and precision, can be the same thing. A bubble is defined as much by its fragility as by its beauty. The very forces that create it, the skin of surface tension, the balance between inner air pressure and outer pull, are stretched so thin that the bubble is never far from vanishing. The wonder of bubbles lies not only in their roundness or their colors, but in their briefness. They are destined to pop. Why do they fail? The answer lies in the slow, invisible thinning of the film. Gravity tugs gently on the liquid, pulling it downward. The top of the bubble becomes thinner as liquid drains away. At the same time, the surrounding air quietly drinks water from the film. Evaporation steals molecules from its surface, thinning it further. What begins as a film, just a few microns thick, dwindles into mere nanometers. Eventually, the film can no longer sustain itself. A speck of dust, a sudden tremor in the air, or even its own exhaustion breaks the balance. The bubble pops. The pop is a small sound, but in physics, it is a dramatic collapse. The surface tension that once held the film taut now pulls it inward violently. The liquid skin contracts, recoiling into tiny droplets that spray into the air. What was a perfect globe of air and water is scattered in a fraction of a second. Children chasing bubbles learn this lesson instinctively. The gentlest touch can burst them. Even approaching too close disturbs the fragile equilibrium. Yet this fragility is not a flaw. It is the natural destiny of a structure stretched to its limit. The bubble is a performance that cannot be sustained. Still, people have long sought to prolong that performance. In the late 19th century, scientists and toy makers discovered a curious additive that gave bubbles longer lives: glycerin. When a little glycerin is mixed into soapy water, it clings to the water molecules, slowing their evaporation. It also makes the film more viscous, more resistant to flow. The result is a bubble that resists drying out, that holds together just a little longer before collapsing. With glycerin, bubbles could last for minutes instead of seconds. This discovery spread quickly into both science and play. Teachers used glycerin-enriched bubbles in classrooms where a bubble could sit long enough to demonstrate interference colors without vanishing mid-lecture. Toy companies adopted the recipe too, producing bubble solutions that children could carry in small bottles, blowing shimmering globes that floated farther and lived longer than those made with soap and water alone. A simple chemical, sweet, syrupy glycerin, gave us more time to marvel at the fragile wonders drifting above us. But fragility in bubbles is not just a curiosity of playthings. It is a principle that echoes throughout biology. The membranes of our cells are, in many ways, soap bubble cousins. Every living cell is enclosed by a delicate boundary made of lipids, molecules with heads that love water and tails that avoid it. When placed in water, they naturally arrange themselves into bilayers, two sheets with tails facing inward and heads facing outward. This bilayer behaves like a soap film. It is flexible, it bends and curves, and it encloses an interior world separate from its environment. Just like a bubble, the cell membrane is a fragile skin, a few nanometers thick, yet vital. It holds together the machinery of life, allowing nutrients to enter, wastes to leave, and signals to pass. It can stretch, fold, pinch, and fuse, much like the soap films Joseph Plateau studied. The resemblance is more than poetic, it is structural. Nature, like a child blowing bubbles, found that enclosing life required a film that could both protect and yield. The connection between bubbles and biology has inspired decades of research. Scientists study artificial lipid vesicles, tiny bubbles of membrane, as models of early life. Some theories of the origin of life suggest that simple lipid films on the early Earth might have formed bubbles spontaneously, enclosing primitive molecules. These fragile spheres could have been the first cells, the first containers of self-sustaining chemistry. In that sense, every bubble floating through the air is a distant echo of life's earliest architecture. The science of fragility extends even further. Foam, countless bubbles clustered together, can form stable structures for surprising lengths of time. In the ocean, foam drifts on waves, clinging to the shore. In certain species, such as some fish and frogs, bubbles are tools of survival. They blow foam nests to protect their eggs, exploiting the balance of surface tension and fragility to create shelters that last just long enough for life to begin. Fragility, then, is not weakness, it is adaptability. The bubble's short life makes it a messenger rather than a monument. Its bursting is part of its message, that balance is temporary, that beauty is fleeting, that structure can be both strong and delicate at once. Scientists have measured this fragility with precision. High-speed cameras show the exact moment of rupture, the film snapping back faster than the blink of an eye. The collapse begins at a single point, a tiny hole opening, and spreads across the surface in microseconds. The speed of this retreat is determined by the surface tension itself. The same force that shaped the bubble now drives its destruction. It is a paradox. The maker of the bubble is also its undoing. What is left after the burst is only memory, the faint spray of droplets, the echo of color. Yet in the laboratory, these collapses have been harnessed. Bubble rupture is studied in physics for its relation to aerosols, in medicine for its role in drug delivery, and even in climate science, where bursting bubbles at the ocean's surface eject salts and organics into the atmosphere, influencing clouds and weather. To watch a bubble pop is to watch fragility reveal its power. The same forces that seem gentle and delicate can, in the right context, shape systems as large as the climate and as intimate as a single cell. And so the bubble teaches us a quiet lesson. Its fragility is not a flaw, but a feature. It reminds us that endurance is not the only form of strength. Sometimes the most delicate structures, a bubble, a membrane, a nest of foam, can shape the course of science and life itself. The child who sighs when a bubble bursts may not know it, but in that moment they are sharing in a truth that has guided physics, chemistry, and biology alike. Fragility is part of the design. It is what allows things to form, to change, to vanish, and to begin again. By the 19th century, soap bubbles had floated far beyond gardens and play. They had entered the laboratory. What had once been dismissed as a child's pastime became a tool for physicists, mathematicians, and lecturers, a delicate but precise way of making nature visible. One of the most remarkable figures in this story was Charles Vernon Boys, a British physicist who, in the 1880s, turned bubbles into instruments of teaching and wonder. Boys had an unusual career. He was known for his experiments with quartz fibers so fine they were almost invisible, which he used in delicate torsion balances. But it was his love of soap bubbles that gave him a lasting reputation with the public. At the Royal Institution in London, the same stage where Michael Faraday had once made audiences gasp with demonstrations of electricity and magnetism, Boys appeared with bowls of soap solution. In his hands, bubbles were not trifles, but gateways into science. He showed how their colors revealed the interference of light, how their shapes followed strict mathematical rules, how their fragility could be extended with careful mixtures. The audience watched shimmering globes rise under the chandeliers, drifting symbols of physics in motion. Boys gathered his knowledge and his demonstrations into a book, Soap Bubbles, Their Colors and the Forces Which Mold Them, published in 1890. The title alone suggested his philosophy, that something so ephemeral was shaped by forces as grand and universal as gravity or electricity. The book became a classic of popular science, introducing readers to the idea that beauty and physics were not separate, but intertwined. The laboratory, too, found new uses for bubbles. One experiment used giant bubble domes to demonstrate atmospheric pressure. By creating large films and drawing air out from beneath them, scientists showed how the weight of the atmosphere could hold or crush delicate structures. The image of a huge bubble trembling under invisible pressure made abstract concepts tangible. Another innovation came in the early 20th century with what were called bubble rafts. These were clusters of bubbles pressed together on the surface of water. When arranged carefully, they mimicked the packing of atoms in a solid. By watching how the bubbles shifted, slipped, or deformed, physicists gained insights into the behavior of crystals and materials. The bubbles, enlarged stand-ins for invisible atoms, gave a kind of magnified view of structures far too small to see. And then, in the mid-20th century, bubbles took on an even more dramatic role. They became part of the search for the smallest building blocks of matter. Physicists invented bubble chambers, large vessels filled with superheated liquid just on the edge of boiling. When a charged particle from a high-energy collision passed through the chamber, it triggered tiny bubbles along its path. Cameras recorded the trails, delicate spirals and curves marking the otherwise invisible passage of subatomic particles. The images were haunting, tracks of ghostly arcs, curls and sudden forks, all written in lines of bubbles. For a moment, the subatomic world became visible through the same fragile phenomenon that children blew from toy wands. Entire discoveries, new particles, new forces, were traced in those ephemeral bubble trails. The detectors were enormous, some the size of rooms, Yet the principle was the same as the shimmering spheres drifting in sunlight. It is curious to think that a child in a garden and a Nobel-winning physicist in a laboratory were, in essence, working with the same phenomenon. The same physics of surface tension, of films and nucleation, tied together toys, classrooms, and the frontiers of science. In this way, the bubble is not only an emblem of fragility, but also of versatility. It could teach a Victorian audience about the wave nature of light. It could model the packing of atoms. It could capture the fleeting traces of particles born in accelerators. Few scientific tools have lived in so many worlds at once. Charles Vernon Boys may not have guessed that his playful lectures would be echoed decades later in particle physics labs. But his conviction was right, that in bubbles one finds not just beauty, but the very forces that mold the universe. One of the strangest discoveries about soap films is that they can solve problems on behalf of mathematicians. Problems that would take pages of equations or hours of calculation are answered instantly when a wire frame is dipped into soapy water. The film that spans the frame arranges itself into the most efficient form, the minimal surface that nature demands. A square wire dipped into soap solution does not simply stretch a flat square across its boundary. The film bows and curves, finding the shape that balances all its forces. A spiral frame produces swirls of translucent sheets, tightening into unexpected patterns. Even elaborate forms, like cubes or polyhedra, yield soap films that settle into surfaces mathematicians might never have predicted. What takes human effort, soap accomplishes in a second. This became a fascination in the 19th century. Joseph Plateau, who had already devoted so much of his life to bubbles, realized that these films were natural demonstrations of geometry. Their shapes were not random. They were mathematical truths made visible in water and soap. The films were obeying the laws of minimal surfaces, where every point is pulled equally in all directions. The insight carried forward into the 20th century, where mathematicians and physicists began to use soap films as tools in research and teaching. They could set up a problem. For example, what is the smallest possible surface that spans this loop? And let the soap film answer. The solution appeared before them, shimmering and delicate, but exact. This is more than a curiosity. It connects directly to one of the great areas of modern mathematics, topology, the study of shapes and surfaces. Minimal surfaces are part of topology's landscape. By observing soap films, mathematicians could see in physical form the same concepts they explored abstractly: curvature, connectedness, boundaries. A wire bent into the shape of a figure 8, dipped into soap, produces a film that bridges the loops with a saddle-like surface. Topologists recognized in these fragile forms echoes of equations written on blackboards. Even more intriguing is the way bubbles behave when they cluster. When two bubbles stick together, their shared wall curves so that the pressure inside each is balanced. When three films meet, they always do so at exactly 120 degrees. When four edges come together, they form the tetrahedral angle of 109.5 degrees. These constants are not approximate. They are universal, precise, dictated by geometry and surface tension. Plateau's laws, established through observation in the 19th century, describe these angles with remarkable accuracy. To look at a cluster of bubbles, then, is to see mathematics at work. The foams that form in a sink of dishes or on the crest of an ocean wave are not chaotic accidents. They are structures governed by deep rules, each junction following the same angles, each surface striving for minimality. Children may poke them for fun, but mathematicians peer into them and find a geometry as strict as any theorem. Over time, these insights inspired unexpected applications. Engineers studying materials used bubble clusters as analogies for the arrangement of grains in metals or the packing of cells in tissues. The geometry of foams informed designs for lightweight structures. Even in architecture, designers drew inspiration from the way films found strength in minimal forms. The curves of certain modern buildings echo the same logic: efficiency, balance, and beauty intertwined. The bubble, then, is not just a fleeting ornament of play. It is a mathematician's assistant, a physicist's model, and an architect's muse. Its fragility hides its power to make visible the invisible logic of surfaces, and there is something humbling in this. With all our instruments and equations, with all our theories and calculations, sometimes nature provides a demonstration that is both simpler and more beautiful. A child can dip a bent paperclip into soap solution and reveal a surface that mathematicians spent centuries trying to describe. This is the paradox that keeps reappearing in the story of bubbles. Their apparent simplicity conceals their depth. A shimmering skin of water can solve problems, teach lessons, and illustrate truths that are otherwise hidden in abstraction. They vanish quickly, but while they last, they carry mathematics on their surface. When we watch bubbles cluster, when we notice the tidy angles where their films meet, we are seeing the work of centuries of geometry. The films do not need chalkboards or proofs. They know instinctively the path of least energy, the shape of least resistance. In that sense, every bubble is both a toy and a theorem, a brief, translucent proof drifting through the air. The story of bubbles does not end in playrooms or laboratories. Their logic carries outward into industry, into biology, and even into the largest questions about the cosmos. For something so fleeting, they have found a place in some of the most practical and profound corners of human knowledge. In industry, the science of bubbles appears under another name: foam physics. A foam is simply a crowd of bubbles packed together, and understanding how they form, persist, and collapse has been vital in countless fields. Detergents, for example, are designed not only to loosen dirt, but also to create stable foams that can carry particles away. The action of soap bubbles is part chemistry, part physics, and entirely essential to the mundane act of cleaning. Firefighting also relies on foams. Special surfactants create dense mats of bubbles that smother flames, cutting off oxygen and cooling surfaces. In this way, bubbles become shields, protecting buildings and lives. The same physics that makes a child's toy sphere shimmer in sunlight becomes, under different circumstances, a weapon against one of nature's fiercest forces. Food science, too, depends on bubbles. The froth on a glass of beer, the rise of bread in an oven, the fluff of whipped cream, all are made possible by gas trapped in delicate films. Bakers, brewers, and chefs are, in their own way, bubble makers. The texture of a loaf, the smoothness of mousse, the stability of a cappuccino's foam all depend on controlling the creation and destruction of bubbles. Without them, food would be duller, flatter, heavier. With them, it becomes light, aerated, alive. Nature has long understood this as well. Many animals use bubbles as tools of survival. Certain fish and insects build bubble nests to protect their eggs. They gather air, coat it in mucus or protein secretions, and weave clusters of bubbles that float on the water's surface. These nests are not strong, but they are sufficient, lasting long enough for the young to hatch in relative safety. Frogs, too, have been observed laying their eggs within foams, fragile shelters that insulate embryos from predators and fluctuations in temperature. The sight is strange: a frog beating its body to whip mucus into froth, then depositing eggs within the bubble mass. Yet it is effective. What looks to us like fragility is, in their world, a strategy of endurance. The foam lasts just long enough for life to continue. The echo between these natural strategies and our own industrial uses is striking. Humans discovered foams for cleaning, protection, and food. Animals had been using them for reproduction and survival long before. The bubble, far from being trivial, has been a tool of life for millions of years. And then, at the farthest scale of all, physicists have imagined bubbles playing a role in the birth of the universe itself. In some cosmological theories, the early universe is described not as smooth and uniform, but as a froth of bubbles. Space-time itself, expanding from the Big Bang, may have undergone transitions where regions of different energy states formed bubble-like domains. Some scientists have speculated that entire universes might exist as bubbles in a vast cosmic foam, each one expanding, colliding, or drifting apart in a higher dimensional space. It is a bold image, the fate of everything compared to the delicate shimmer of a soap bubble. But the analogy is not whimsical. The same mathematics that governs minimal surfaces and thin films can be applied in altered form to the physics of fields and space-time. The geometry of a child's toy becomes a metaphor for the architecture of reality. What unites all these examples, from detergents to frogs, from cappuccinos to cosmology, is the recognition that bubbles embody balance. They are fragile, yes, but they are also efficient, adaptable, and revealing. They show how nature manages the interplay of forces, how thin boundaries can enclose and protect, how small things can reflect great truths. To look at a bubble is to see not just a sphere of air and soap, but a principle of design repeated at every scale. It is cleaning a dish, feeding a child, saving a forest from fire. It is a frog's nest, a fish's refuge, a scientist's model of the universe, all of them fleeting, all of them shimmering with meaning. And so, when a bubble floats past, glistening in the light before it vanishes, it carries with it not only the laughter of children or the experiments of physicists. It carries a lineage of science and survival, of play and necessity, of the smallest details and the grandest ideas. For a moment, in its fragile film, the world is reflected whole. Picture again that child in the garden, holding a wand, blowing a shimmering globe into the air. For a few seconds it drifts, shining with impossible colors, delicate as breath itself, and then it vanishes with a faint pop. It seems like nothing, a moment too brief to matter. But inside that moment is centuries of science. Newton saw colors in thin films and wondered at their cause. Thomas Young proved the wave nature of light with patterns like those painted on bubbles. Joseph Plateau gave his sight to studying their fragile surfaces, and Charles Vernon Boys filled lecture halls with their shimmering lessons. In laboratories, bubbles modeled crystals, revealed minimal surfaces, and even traced the paths of subatomic particles. In kitchens, they give us bread and beer. In forests and ponds, they shelter the beginnings of new life. And in the imaginations of physicists, bubbles stretch outward to describe the very fabric of the universe. A soap bubble lives for seconds. Yet in those seconds, it reveals the pull of molecules, the play of light, the rules of geometry, the resilience of life, and the shape of the cosmos. It is both trivial and profound, a toy and a teacher. So, the next time you see a bubble drift past, remember that you are watching physics itself, suspended for a heartbeat in the air. Something so ordinary, so temporary, carrying within it the weight of centuries and the reach of the infinite. Bubbles remind us that the deepest truths are not always hidden in the distant or the grand. Sometimes they are waiting quietly in the most fragile, fleeting things.